In this video, we're looking at the derivative of a function. So this is going to be a new concept. This is our first true new calculus type of stuff. Now, limits were, the introduction of this. Limits aren't truly calculus. They're more of why calculus works, but this is our first foray into true calculus. We are going to now use the limit to define the slope of a tangent line, right? But we're also going to use this to define what's called differentiation. So the definition of a derivative is basically the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So that slope of the tangent line, that is what we're going to call the derivative. Okay, not at a specific point, but just general. In general, at any location, the derivative of a function is the slope of the tangent line. Okay, now notice how it's written. Let me get back to my pen. See this? F prime of x. This is how we are going to write a derivative. So anytime you see f prime of x, this doesn't mean anything other than the first derivative, okay? So the derivative of f is the limit of the difference quotient as delta x approaches 0. And this is providing that the limit exists, okay? Now, be sure to see that the derivative of the function is also a function of x, right? If we take the derivative of a function, we're still going to get something that has x in it, right? The new function is given that slope of the tangent line that we talked about at the point x f of x. Any given x f of x, provided that the graph has a tangent line at that point. The derivative can also be used to determine what's called instantaneous rate of change, or simply rate of change, of one variable with respect to another one. Now, the process of finding the derivative of a function is called differentiation. And a function is considered differentiable at x when the derivative exists there, and it's differentiable on an open interval from a to b when it's differentiable at every point in that interval. Notice we're using an open interval. All right? Now, in addition to f prime of x, which we can call f prime of x, right? We can write it with f like an apostrophe and then parentheses x. There are other ways of writing the derivative. Now, most of the time, we're talking about f of x, right? So we'll say f prime of x. We'll also write it as dy over dx. Doesn't that look an awful lot like delta y over delta x? But delta just means change in. So isn't this y2 minus y1 over x2 minus x? And that slope, hey, we're back to one of the other ways of defining that slope of the tangent line, right? So we also have just y prime, because y equals f of x. We can also d of x of f of x. So this is the derivative. We'll say this is the derivative of this with respect to this. So the derivative of f of x with respect to x. And that's what they all mean. We're going to say the derivative of y with respect to x. We also could just say dy dx. A lot of times we use, these are going to be our most common ways of writing derivative. We'll see this one a little bit more when we're taking derivatives of big functions inside of things. It'll happen. This you hardly see at all in this class. It'll pop up a little bit later in higher maths. You'll see that notation, but here we're going to pretty much stick to these three. Now notice that we're going to write it using the limit notation. It would just be dy dx equals the limit of delta y over delta x as delta x approaches 0, which is just that difference quotient, which is get us back to f prime, right? So let's use the definition of the derivative as shown here as the difference quotient, the limit as delta x approaches 0 of the difference quotient, and find the derivative of x cubed plus 2x. So we need to know what f of x plus delta x is, minus f of x all over delta x. So let's define f of x plus delta x. That means we're going to have to plug in x plus delta x anywhere there's a x. So x plus delta x cubed plus 2 times x plus delta x. So x plus delta x would give us x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. And then we distribute that 2x plus 2 delta x. If you don't know why that's the case, you can, of course, always just FOIL it out, distribute it, get that. Or if you remember from pre-cal, you can use Pascal's triangle to get those coefficients, and then use the rule for creating a binomial expansion to get the terms. Totally up to you on how you do it, but that's going to be your answer. So that gives us nothing that will combine, so we have to leave that alone. We know that f of x is just the function itself, x cubed plus 2x. So now we can take the limit as delta x approaches 0 of f of x plus delta x, or x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2x plus 2 delta x minus f of x. So minus x cubed plus 2x. And notice that I put that in parentheses because I need to distribute the minus sign all over delta x. So this is going to give us negative x cubed, which will cancel out with positive x cubed. This will give us negative 2x, which will cancel out with positive 2x. So now what we have is the limit as delta x approaches 0 of 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x all over delta x. So we factor out our delta x. That's left, leaves us with limit as delta x approaches 0 of delta x times 3x squared plus 3x delta x plus delta x squared plus 2 all over delta x, right? I just factored a delta x out of each one of those. Those cancel out. I've got the limit as delta x approaches 0 of 3x squared plus 3x delta x plus delta x squared plus 2. So at this point, this is just a polynomial, so we can plug in delta x equals 0. So that goes to 0, that goes to 0, and all we're left with is 3x squared plus 2. So you're going to want to do quite a few of these to make sure you understand the process behind using the limit to find the derivative. If you have any questions about it, don't hesitate to shoot me a reminder or ask a question in class.